Okay.
All right. So thank you very much for, well, to Juan especially for inviting me. I know it's the wrong time of the day for him, so that's okay. My name is Paul Lasky. I'm a associate professor at Monash University in Australia. I work on all forms of gravitational wave science, from LIGO the whole way down to pulsar timing arrays, with a particular focus often on neutron stars and neutron star physics and what we can learn about neutron star science. So allow me to share my screen. Hopefully everyone can see that. I'll put it into full screen. Please feel free to stop me at any point during the talk, and we can. I'm more than happy to have a discussion, as opposed to this just being a one-way presentation. So if anyone would like clarity on anything, then they should absolutely feel free to stop me as we go. What I want to talk about today is basically physics from binary neutron star mergers, and what I'm really going to focus on is what we can learn from gravitational wave observations only. I believe there's a talk coming up next, which is going to be about more on the nucleosynthesis side, and so associated with Kilonova observations potentially and things along those lines. Tim Dietrich is going to talk, I believe, later today, more about the numerical relativity side of things. So I'm sort of more focusing on saying, okay, given we're observing lots and lots of events with gravitational wave observatories now, with neutron stars involved, what kind of science can we learn about with those neutron stars, or about those neutron stars with those gravitational wave observations? As I was writing the talk, it occurred to me that we actually have so many observations already that there's this beautiful wealth of things to talk about. So it's probably going to be less about what's going to happen in the future and more about what are the really interesting observations that we've seen up until this point, and how do we interpret some of those. And, you know, to some degree, we have no idea what's going on with a lot of those observations. And that really is a great thing. So this diagram here on my front page, I will show a little bit throughout the talk. It's a really beautiful schematic that a artist in residence put out or produced for us. And his name is Carl Knox. And he made this gorgeous graphic, which now appears in a review that I wrote with my now former PhD student, Nikhil Saran. And that's a review on post-merger remnants. So just to very, very quickly walk through this diagram, what you see here on the left-hand side, and again, hopefully you can see my mouse. On the left-hand side, you can see two neutron stars and they're spiraling in on one another. And this is the gravitational wave signal that we're used to seeing. And we've seen this now a few times, and I'll talk a little bit about that. The neutron stars here are represented as cold things. They're represented blue. I know blue is not necessarily cold. There's some artistic license here, but they're really cold in that sense because they're old, they're dead neutron stars. And so they've been around for a long time, just coalescing slowly in amongst one another, into one another. These two neutron stars then merge, highly dynamic state, and we'll talk a little bit about that as we go. And then there's these multiple pathways that the neutron star, the remnant, can take. And if that neutron star is over a certain mass, it will just immediately collapse into a black hole. It'll launch a jet. We'll see that jet maybe if it's facing towards Earth as a short gamma ray burst. And then the system pretty much settles down. You've got maybe an accretion torus, which will survive for some short amount of time. Not all that many interesting things happen. But there's another scenario whereby if the mass is below some certain threshold, and we might talk a little bit about this, but I'm happy to discuss it in detail. If the mass is below some threshold, then rather than forming a black hole immediately, you're actually going to form this new neutron star. It's going to be massive. It's going to be, 2.5, 3.5 solar masses, and it'll be supported by its centrifugal support. So it'll be supported because it's rapidly rotating. It's incredibly hot. It's got huge magnetic fields. So you can see in this diagram, it's represented as being, quote unquote, hot because the as this sort of really red color. It's going to have, again, an accretion torus around it. Maybe it launches a jet. Maybe it doesn't. We don't actually know. That thing, though, as I said, it's really massive. So that could be above the maximum mass that neutron stars can support, in which case it will eventually collapse to a black hole. And that's what we're showing here in these sort of other bifurcations, which I'm not actually going to talk about in too much detail today. but I do work on these sort of right-hand side phases of this diagram, and I'd be happy to answer questions about it. But the thing I really want to focus on is these sort of first 4 stages here, A, B, C, D. And the reason that I want to focus on that today is that we're going to talk about it in the context of gravitational wave observations. So, of course, these are 3 beautiful photos of 3 gravitational wave observatories, LIGO Hanford up in the northwest of the US, LIGO Livingston down in the south, 1,000 kilometers away from LIGO Hanford. And then there's the Virgo site, which is out near Pisa in Italy. And these 3 gravitational wave interferometers have been operating now for 5 or 6 years at sort of in what's called the advanced era and making beautiful detections. And of course, the most famous of all of these gravitational wave detections is this one from 14th of September 2015. It's hard to believe it's more than 6 years ago now, but this is sort of the most beautiful observations. This is the first direct observations of gravitational waves. It's the first direct observations of 2 black holes. I'm not going to walk through the details of this. Hopefully you've all seen this all before, but this is, just to really highlight that this is what we see when we in a gravitational wave observatory. Now, it's worth noting that the data here on the top left is what was seen in Hanford in Washington. It's been cleaned up in ways that I don't want to get into in the details of today's presentation, but this is not necessarily what you see in terms of raw output from an interferometer like this. But what is remarkable is when you clean up this data in this way and you superimpose what was seen in Hanford on the data that was seen 1,000 kilometers away in Livingston, then you get these absolutely beautiful features that directly overlap, and you see these amazing gravitational wave signals, which are exactly what we predicted. I like to give a very brief schematic of how LIGO works. And I tried asking my boss at Monash University to, fund an interferometer for us, and he basically threw a whole bunch of Lego at me. And so this is the best we could do. This is my schematic of how these LIGO interferometers work. And of course, if a gravitational wave comes into an interferometer like this, then the interferometer starts moving. Not to scale, but this is sort of the whole idea of what a gravitational wave interferometer does. And so you can measure these changes in arm lengths. Let me skip right past that though and mention something important about gravitational waves. And what I'm going to talk about in what follows is a little bit about how we learn science from gravitational wave observations. So it's all very well to say that, we collect these wiggles, we see these wiggles in our gravitational wave instrument. What does that mean? How do I know that, this, for example, 150914, this was 2 black holes. They had a mass of 34 solar masses each. They were located in a certain region on the sky. How do I know these things? Okay. And this is really an interesting question. This is something that we call parameter estimation in the gravitational wave community. And I just want to have a very brief introduction to this idea of parameter estimation. And the reason I want to talk about this is later on when we talk about colliding neutron stars, for example, we can also talk about what kind of measurements we can make. And it's using this exact same technique. So, here is my sort of 1-slide introduction to gravitational wave Bayesian parameter estimation, and I say it's done wrong. This is my 1-slide introduction that uses something called Goldilocks, and it occurred to me as I was putting these slides together earlier today, or finalizing the slides, that I'm not sure if Goldilocks translates in Spanish or if the story is even told. So I got on Slack with Juan, and he told me that this Spanish expression up here would be something everyone would know. I hope you're not all laughing at me so I'm just going to, plow ahead. And if this is complete nonsense and garbage, then you're going to have to blame Juan. Maybe that's why he's not turned up at the moment. But this is the 1-slide introduction. Okay, so what we have in the background here is our gravitational wave data. This is what we collect off the instrument. And what I can do is I can calculate what I expect a gravitational wave signal to look like when, in this case, 2 black holes coalesce and ultimately merge. And so what I can then do is I can get that calculation of gravitational wave signal, and I can overlay it on my data. Okay, and what you see here is that this is just a really rough example of what a gravitational wave signal would look like. And I can try and match up the peaks here, for example. And what you can see is that the peaks are sort of too spread out, right? So there's a peak in the gravitational wave signal about here where my mouse is. There's another peak about here, but of course, the actual prediction that I had here, or the gravitational waveform that I'm showing in white, that's actually spread out too much. So in other words, the gravitational wave frequency for this waveform is too small, or in other words, in the Goldilocks sense of the porridge is too hot. In that sense, the masses here are too high. Okay, so the masses are too high, the frequency is too small, this waveform is all wrong. And so what you can do is you can play this game of saying, okay, well, what about a different waveform? I can look at a waveform like this and I go, oh, hang on, the frequency now is too high, right? The individual peaks between each waveform don't match up with the data that I'm getting, therefore the masses are too low. Okay, the porridge is too cold, the masses are too low. All right. And so you end up playing this game and you've got actually about 15 or 17 or anywhere up to 19 parameters that describe this gravitational waveform. It's not just the masses, but it's the sky location. It's the inclination angle of the binary with respect to your line of sight. It's that time of coalescence. It's all of these different parameters, the distance to the source, all of these different parameters. And you end up basically trying to fit this 15-dimensional parameter space. And again, it depends on what kind of quantities you want to count, but it's between 15 and sort of 17 or even up to 19 dimensional parameter space to find that maximum likelihood waveform. Okay, so obviously this is the Goldilocks version, but ultimately this is done with Bayesian parameter estimation. And so you can actually end up deriving a posterior probability distribution for each of the individual parameters that go into your model. So you end up deriving a probability that the primary mass or the heaviest mass of the black hole was such and such a mass, and you get a maximum posteriorized, et cetera, et cetera. So one thing I just really want to quickly advertise is that we've built some software that makes this actually really easy to do. And so if you want to have a go at your own version of Bayesian inference for gravitational wave data, then we've built this software called Bilby. Bilby is a really cute, fluffy animal that kind of looks like a kangaroo, but it's much, much, much smaller. So we named it after this cute, fluffy Australian animal. But in reality, it stands for Bayesian Inference Library. And this is actually the software now that the LIGO and Virgo collaboration use to perform this parameter estimation. And so as an example, one thing that you could do is you could very easily take the data from 150914, which is what we've got here, and you could say, okay, well, I can run this parameter estimation software, and there's all these examples of how to do it. And I'm not going to show you the output plots from that. I'm going to show you actually the original output from the workhorse parameter estimation software that called LAL Inference that was the collaboration earlier used. But with this parameter estimation idea, what you can do is you can say, okay, I can actually measure the masses. And so you end up with this posterior probability distribution, or in other words, you end up working out what the masses of the two black holes that merged were in a system like this, okay? And so what you can see with 150914, you've got the more massive object was something like 36 solar masses plus or minus 4 or 5 solar masses. The secondary mass was 29 solar masses plus or minus 4 or 5 solar masses as well. And you get this joint probability distribution for the masses as an example. Another thing that you work out is how far away this object was. And of course, you actually work out that the distance to the object is degenerate with the inclination angle to it. No, I don't want to go into all of these details. They're not too important for the talk at the moment, but just to highlight these types of things. The other thing that, of course, you can work out with this parameter estimation is you can work out where in the sky it came from. And so this is a map of the sky with the posterior probability distribution of where this object came from in the sky. And of course, when I have two neutron stars merging, this is really important because rather than being able to say it came from this huge region of sky over in this, southwestern hemisphere somewhere, with a binary neutron star merger, what you actually want to say is, actually, it comes from this really small sky area, maybe tens of square degrees, and therefore I can point all my telescopes, my electromagnetic telescopes, and at that small patch of sky and work out where the gravitational waves came from. So this is the game that we sort of play now with the LIGO and Virgo collaboration. And of course, there's been a really successful case of that, and I'll talk about that shortly. But I do first want to mention, okay, we can go out, we can measure these gravitational wave sources, and I've talked about we can measure their masses. And I really want to focus on their masses, at least at the start, because the masses are the things that, at least in some sense, tell us if they're neutron stars or black holes. So what do the results look like? Well, the LIGO and Virgo collaboration have got 3 what are called gravitational wave transient catalogs. And so this is essentially 3 sets of data that have been released with all of the results. And the third one was just released very recently. And what I'm going to show you is this beautiful plot that gets made, which is called Masses in the Stellar Graveyard. And it really highlights what kind of objects we're seeing and the masses of them. So what I'm showing here first is just the first objects that were observed as part of this first gravitational wave transient catalog. So this is taking us back a few years now. It's essentially the first 10 events. And you can see the first event that was ever measured was this 150914 event. It's the one far left. And so what this looks like is the blue dot down the bottom was that secondary mass object. It was that 29 solar mass, approximately black hole, merged with a 35 solar mass black hole, and they created a 60 or 70 solar mass black hole. And so this is how I read a diagram like this. And so what you can see is out of those first 10 or 11 events, these are all massive black hole mergers that are around about 10 or so solar masses, 10 to 50 solar masses, okay, except for this one of them, right? And there's this one little outlier here, which is the very famous 1708-17, and we'll talk about that shortly. But 1708-17, rather than being colored blue here, they're colored in orange because they were 2 neutron stars that merged. So the masses of these were a lot smaller. In the spirit of Goldilocks, the porridge was too hot. The gravitational wave frequency was really, really high, okay? This thing was in the band for a long time, and we'll talk about all of these kinds of things. But that gravitational wave signal indicated that it was actually 2 neutron stars. Now, one thing I'll discuss in a little bit is that you can see that the remnant here, so 2 neutron stars merged, the remnant here is colored half orange and half blue, and that's because we don't actually know what that merger remnant was. Now, if you want to understand neutron star physics, and if you want to get at things like the equation of state of nuclear physics at supernuclear densities, this is where you want to start looking. You want to start understanding the remnant of objects like this to really understand nuclear physics in the most extreme regions of the universe. But let's get back to that. So that was the first gravitational wave catalog. The second catalog fills this diagram out considerably, and there's a whole bunch more interesting events. But there's another interesting event called 1904-25. I believe this one up here is 1905-21, which was the most massive binary black hole merger. There's so much interesting science about that, but this is a neutron star discussion, not a massive intermediate mass black hole discussion. Then there's these other 2 really interesting events here. One of them is 1908-14. And again, you can see that actually this time the merging mass, so the lighter of the 2 objects that merged, is colored in half blue and half orange. And I'll talk about that in some detail in a second. 1904-26 kind of looks like it's the first ever neutron star merger with a black hole, so a neutron star black hole binary. And in fact, it could be. It's sort of argued there's a low, relatively high probability that that's not actually a real event, but it's that's one for the statisticians. But it doesn't matter because we do have Bonafide now. We do have Bonafide neutron star black hole mergers. So there you can see now, completely filled out this diagram, there's something like 90 gravitational wave signals that have been detected in the last 6 years alone. There's this, I think this one is GW191219, doesn't get much attention, but this GW200115 is a neutron star black hole binary that was published as such, as was GW200210. And so these are sort of really, really interesting events. And again, I'll talk about these as we go through. So this is really the state of the art now. And when I say state of the art, that last section of the diagram was just filled in the paper was put on the archive. I believe it was last week, and there was some really good press coverage around that and things along those lines. But some really, really interesting science to come out of all of that. I'm not going to talk too much about all of black holes. You can see that there's a huge amount of information there in terms of black hole science. But of course, this is more of a workshop on neutron stars. So let's focus in on those neutron stars. I've mentioned this diagram in some detail. And the reason I'm bringing it back up, actually, I didn't want to skip straight through that, is this is the phase that is very well known and is very well understood in terms of the gravitational wave signal. So I have two neutron stars, they're spiraling in on one another. The gravitational wave frequency, and you can see I'm plotting here, if we just look at, for example, the red curve, the gravitational wave frequency, as these two objects gets closer and closer together, the frequency increases, the amplitude of the signal also increases. But there's another really, really interesting feature here that you can start to get at that depends actually now on the nuclear equation of state. Okay, so this is now when we're getting to the meats and bones of gravitational wave astronomy in terms of supranuclear densities and nuclear physics, is that you can see that there are two curves here. The red curve is a gravitational wave signal if we just assume that these two things are point masses. So in other words, if we just assume that they're two black holes that are merging, then we would get this red gravitational wave signal. If on the other hand, we say, they're not black holes, but they're neutron stars. So in other words, they're elongated objects, they're structured objects, then you would actually have this black curve. And so the fact that there is this tidal deformation pulls away energy from the system, okay? And so in essence, what happens is the system merges quicker. Now, in terms of all of that parameter estimation that we were talking about, you can actually work out and introduce this extra parameter, or in fact, two extra parameters into your waveform model to understand how quickly these things merge as a function of what the equation of state is. And this is something that we call the tidal deformability. Okay, so you can imagine if I have a softer equation of state, a softer equation of state means my neutron star is smaller, okay? If I have a smaller neutron star, then it doesn't deform as much due to the gravitational field of the other objects. And then therefore the merger will take longer. It'll look more and more like a point mass merger. And this whole idea is quantified by something that we call this gravitational wave, or this tidal deformability, lambda. And so lambda, you get a lambda, there's a subscript I on that because I have lambda for one of my neutron stars, I have a lambda for the other neutron star, so I get two lambda parameters that I need to go into my parameter estimation or into my waveform model. And what you can see is that this lambda is a function of the star's radius, okay? It's a function of the star's mass, and it's a function of the star's Love number. So the Love number is just a way of measuring, how much an object reacts to being in a tidal field, how much it sort of deforms when it's in a tidal field. And so you can see, of course, if you know the mass and the radius and the Love number, that's effectively what an equation of state tells you. Okay. So in other words, once I know what lambda is, and for example, I measure simultaneously lambda and the mass, then I can measure the radius and the Love number, and then I'm starting to get at what the equation of state is. And I'll show you some results of that very, very shortly. So I've written there more fluffy neutron stars are deformed more. And what I mean by fluffy is just these puffed up things, something that might be 20-kilometer radius rather than a 10-kilometer radius, or in other words, a stiffer equation of state. They're going to be deformed more, and therefore they're going to merge earlier. So that's really the first phase of gravitational wave astronomy from these two merging neutron stars, where I can start to learn about the equation of state. And we've done this, and I'll show you this in a second. But for me, what's even more interesting is one thing that we haven't yet done, and it's this next phase of this diagram. So if I remember, we talked about how two neutron stars merge and they actually merge into one neutron star. And if they're below some certain mass, then you'll get this really hot remnant and it's really massive. And it actually turns out that this thing is highly dynamic and it's emitting really, really strong gravitational waves and they're really, really high frequency. So this is a plot from a number of years ago from one of Jocelyn Reed's papers on this topic. And all it shows is the gravitational wave strain. So basically the gravitational waves that are emitted as a function of the gravitational wave frequency. And what you can see is those frequencies are really high. So they're up in the kilohertz regime. And the 4 different curves represent the gravitational waves that you would get for 4 different types of equations of state. Okay. And so you can see there's for those who know their acronyms, there's an SLY equation of state, APR4, H4, GAM2. It doesn't really matter. The whole point is the different equations of state actually give you different merger frequencies. And that's the crucial thing. So you can see that the equation of state here, this purple curve, has a dominant merger frequency around about 2 kilohertz. H4 has a dominant merger frequency around about 2.5 kilohertz. And the other two are a bit higher, up at the 3 kilohertz regime. So if you can go away and measure these gravitational waves, then actually you can measure the equation of state really, really well. Okay, it actually depends really sensitively on the equation of state. Now, this is a paper from Jocelyn's work some 8 years ago. The field has advanced a lot in this time, and we understand what those frequencies are and how they correlate to what the equation of state should look like. We understand lots of those details. We understand how to search for these gravitational waves, but we have never seen them. Okay, and yet we're not that far away from desired sensitivity to be able to see them, but we would need to get very, very, very lucky. And I think it's probably still about 5 years away, but this is certainly one to watch in the future. And there's actually a really interesting reason why this is one to watch in the future, and it's that this state of the neutron star post merger is really, really hot. It's some many times 10 to the 10 Kelvin or tens to 50 MeV for those that like to talk in that language. So it's incredibly hot. So if I sort of advance the slide, you can see up here on the right-hand diagram, I've just included a random phase diagram. Okay, and this phase diagram shows, temperature as a function of density. We live somewhere down on this really boring bottom left-hand corner. Neutron stars, the old cold neutron stars live in this really high density regime, but at practically 0 temperature. So the point is when the 2 neutron stars are in spiraling, so in this phase A here, and when I measure the tidal deformability, they are on the bottom of this phase diagram. But when I measure the gravitational waves at this post-merger remnant, when it's really, really hot, all of a sudden it's jumped up in this phase diagram. And you can see that if you're going to have any kind of deconfined quarks in the core of your star, if you're going to have some kind of quark gluon plasma, if you're going to have any of these exotic states, like perhaps color superconductors or anything like that, that could happen as a function of temperature. So the point is, if I get a temperature-dependent phase transition in the core of the neutron star, then that's actually something I can measure, and I can measure it. And this is just a beautiful paper here by Andy Bauswan, from a couple of years ago, but there's a considerable amount of work on this now. But this paper shows you that actually I can measure the in spiral, okay, and what the gravitational wave frequency peak I expect from the in spiral as a function of this tidal deformability should sit really nicely along this gray curve. But the point is, I can actually measure this gravitational wave peak frequency, and if it jumps up off this gray curve, then that's actually a signature that there's a temperature-dependent phase transition, okay? And so this is a really solid way when you measure both the in-spiral gravitational wave signal and that post-merger. There's a really interesting way here of getting at those potential temperature-dependent phase transitions that you really have no other way of getting at in bulk nuclear matter anywhere else in the universe. So this is a sort of really powerful driver for getting that high frequency part of the gravitational wave signal, which is something I could talk for absolutely days on end, but I won't bore you with it, but please feel free to ask me about it afterwards. It would be remiss to not say something about this post-merger phase and sort of the late time post-merger phase. We see observations of this phase in terms of X-ray observations of gamma ray burst afterglows and things like that. I'm not going to go into details here other than to say gravitational waves are also emitted during this regime, but they're very likely very weak. And so it's probable that we won't see gravitational waves in this regime anytime in the next 10 years would be where my money goes. That's if I had to bet my house on it, I would say we're not going to see them in the next 10 years. I hope to be proven wrong, although I hope no one takes my house because of it. But I think these gravitational waves are just far too weak and far too difficult to detect. Okay, which is not to say there's not interesting physics about equations of state and all those kinds of things, but for another time perhaps. So let's go back and talk about gravitational wave observations that we've actually seen, and what have we actually learned about the physics of neutron stars from these gravitational wave observations. So what I'm showing here now is we talked about GW 170817. This is this very iconic event from the 17th of August in 2017, 4 years ago now. And what you can see on the bottom plot here is the gravitational wave time frequency map. So this is just gravitational wave frequency on the vertical axis, time on the horizontal axis, and you can see this really beautiful and loud and clear trace. So the thing enters this graph at least 10 seconds before the merger. Actually, it was in the LIGO band probably for a whole minute before the merger, maybe up to 90 seconds before the merger. But you see that the gravitational wave signal comes in and it chirps upwards. And that's where this frequency of merger comes in. The gravitational wave frequency at merger is up in the kilohertz regime, but we lose sensitivity at that regime with the LIGO interferometers in their current status. So we don't actually see the final merger, but we certainly see that late in spiral. And what I'm showing you now on the top three panels are gamma ray observations from three different instruments. So two of them on board Fermi, and they're different frequency bands for their what's called GBM, or the gamma ray burst monitor. And then on the bottom panel, the second bottom panel, is the light curve from another hard X-ray instrument called Integral. And what you can see is they have just background noise. There's nothing really interesting in any of these detectors, even through that merger phase. But all of a sudden, about 1.5 to 2 seconds after the gravitational wave inferred merger time, you see this excess of gamma rays. And this is, in fact, the very famous gamma ray burst, and it's called GRB 1708-17A. So this is the gamma ray burst that was associated with the gravitational wave signal 1708-17. And this is actually the first time that we ever saw electromagnetic photons coming from the same location as a gravitational wave signal. But the story, of course, doesn't end there. What else did we see? Whoops, that went the wrong way. Here I'm showing you a picture of a very ordinary galaxy called NGC 4993. And this is a picture taken with the Hubble Space Telescope from a couple of months before this gravitational wave merger. And there's nothing so exciting. But here is a picture taken of the same galaxy. And this is taken by a 1 meter telescope in Chile called the SWOPE telescope. But there were many others. And what you can see is this is exactly the same galaxy taken 11 hours after the merger. And of course, it's got the same central blob. It's got the same sort of foreground stars and all of these kinds of things. But there's a new point here, which is indicated by that big red arrow. And that's actually the afterglow. And in fact, it's the Kilonova signal from that gravitational wave merger. I do believe the next talk is going to be all about nucleosynthesis, and so they might go into a lot more detail about this object and this sort of optical photons and things, so I won't talk about that. But just to say that you can learn, obviously, a lot about nucleosynthesis of heavy elements, but you can also learn about the equation of state and learn about nuclear matter as well from Kilonova observations. What I want to focus on, though, is what did we learn in terms of gravitational wave signals only? And so from the gravitational wave signal, as I mentioned, we measured this in spiral. You can see, again, this is the last 10 seconds of that in spiral signal that we saw. And doing that parameter estimation that we talked about earlier, you can actually work out, of course, the masses of the two objects, okay? And this is a somewhat complicated plot, but if we focus just for the moment on the blue curves, and then I'll talk about the red curves in a second, if we focus on the blue curves, you can see that the most massive neutron star here was around about 1.5 solar masses. It was about between 1.3 and 1.6, 1.7 solar masses, give or take. And the secondary neutron star was between about 1.4 and 1.1 solar masses, give or take. So if you know anything about neutron star astronomy, this is pretty garden variety neutron star masses. There's nothing unexpected. We've measured lots of masses of neutron stars in our galaxy in double neutron star systems, and this is fully consistent with that. Now, the blue compared to the red is just an approximation that you make about how these two stars are spinning. And if you actually allow for the fact that they could have been rapidly rotating as they were merging in, then that becomes a little bit covariant with the mass measurements. And so you lose a little bit of information. So if you sort of relax your priors on this, what you think about the neutron star spins, then you get these much bigger posterior distributions, which, you know, more massive for the primary, less massive for the secondary. I don't think many people believe these red curves as opposed to believing the blue curves, but in the spirit of completeness, it's absolutely worth showing. Okay, but obviously that's not the thing that we came for necessarily. Absolutely, we want to know the masses, but what about this tidal deformability? So here's a plot which is probably not all that exciting, but it tells us what the posterior distribution is for the tidal deformability of those two neutron stars. And if you remember, the tidal deformability equals 0 means that the object is a black hole. Okay, so when the tidal deformability is 0, in other words, at the very bottom left hand of this diagram, that means that this is a black hole. You just from the gravitational wave data alone, even with such a loud event like 1708-17, we don't actually rule out these being black holes by themselves. Okay, of course, the electromagnetic observations do rule that out, but just from the gravitational wave observations, we don't. So what you can do is you can put various equations of state on here. You can see that large values for the tidal deformability are ruled out. The 50% contour is somewhere around here, which, you know, rules out really sort of stiff equations of state, but sort of is more in favor of more compact equations of state. Now, personally, I've been staring at diagrams for like this for a long time. I don't find them all that helpful. What I do find helpful what might even seem like more confusing curves, but hopefully you've seen a few of these in the earlier in this week. And this is just a typical mass radius diagram with very different equations of state being shown here. So each different curve on here is a prediction for what neutron star masses and radii should be given that equation of state prescription. And what we can do is we can start putting constraints on a diagram like this from various observations that we have of neutron stars throughout the universe. So we can start off by just saying, okay, we observe pulsars, and there's this one reasonably recent measurement from about a year ago from Thankful Chromati. So this pulsar J0740, which has a mass of around about 2.2 solar masses. And so what you say is, okay, I've got this, I can put this purple strip across the top of this diagram, and any equation of state that doesn't go high enough to get into this region is ruled out because it can't create a neutron star that's that massive. So for example, there's this whatever color blue that is that just gets up here to just less than 2 solar masses. That's practically ruled out. This red equation of state, that's ruled out. You know, you can start to rule out equations of state in this way. That's just the heaviest neutron star that we've observed. Of course, this is now the constraint that you get from taking that tidal deformability with 1708-17 and converting it into a constraint on the radius of the neutron stars. And what you get, and this is just a sort of very rough approximation, but you end up ruling out anything sort of to the right of this diagram. So all of these equations of state here that predict, at least for neutron stars with 1 to 1.5 solar masses, predict neutron star radii between 10 to 14 kilometers, they're all still good to go. Okay. Now, it would be remiss of me at this point not to say, well, what happens when I take the recent, relatively recent X-ray data from the NICE mission. And this is where you time X-ray observations, you time a neutron star J0030, and they actually get much tighter constraints than what we have just from LIGO measurements. But indeed, they're absolutely complementary because their constraints are very much model dependent. Now, we played a game, I think it was a year or so ago as well, of saying, okay, we got a constraint like this blue curve from GW 170817. What do we get if we look forward, say 3 to 5 years, if we've got 40, not just one, but 40 gravitational wave observations of binary neutron star mergers, and it turns out that we get constraints that are sort of very similar to those nicer constraints. So in other words, in about 2 to 3 to 4 to 5 years, maybe, we would expect to have constraints on the neutron star equation of state comparable to those that you get from NICER, but in a very complementary way. Okay, so I'll say a couple more things just about the post-merger signal, and then talk very quickly about neutron star black hole binaries or other systems as well. That looks like I've lost a bit of a plot here. Don't worry about these plots. I'm not sure if that's showing up on your screen properly, but it's definitely not showing up on my screen. We searched for gravitational waves from the immediate aftermath of 170817, and we didn't see anything. And it turns out we're about a factor of 30 to 40 away in sensitivity from being able to see anything. So I think it's still sort of 5 to 10 years away from being able to see gravitational waves from this post-merger remnant. Having said that, you can learn about the post-merger remnant from the Kilonova signal. And so that's what I'm showing here is the Kilonova spectrum over a period of sort of days after the 1708-17 merger. And it turns out that actually the color of this Kilonova signal, the fact that it's got this blue bump at early times, actually indicates that a neutron star survived that collision for at least some period of time. And again, I can go into the details of that if people are interested. But the color of that kilonova is providing tentative hints towards nuclear equation of state type of measurements in terms of telling you what the mass of the remnant neutron star would be and how long it survived as a neutron star before it likely collapsed into a black hole. I'm sort of running out on time, so I'll just sort of sum up this by saying we have absolutely no idea what really happened to the remnant of the 1708-17 merger. It might have formed a short-lived neutron star. Some authors believe it formed a long-lived neutron star, but we don't really know, and there's a lot of ongoing work to try and understand this. I'll also skip over that, and I think I might end on this slide and then sort of open up for questions and things if people are interested. I want to really just mention that one of the more fascinating observations that we've had that maybe doesn't get enough coverage, but in terms of nuclear physics, this could be the most interesting observation, at least in my mind. We observed this system called GW 1908-14. And 1908-14 has a really sort of large mass ratio. So the heaviest object is about 23 solar masses. So it's quite a heavy black hole. But the secondary object, this is the mass of the secondary object. And the two different colors just represent different sort of systematics in our analyses. But what you can see is that the mass of this object is around about 2.5 to 2.7 solar masses. Now, you can argue that this is one of two things. First, you can argue that it's the heaviest ever neutron star that we've observed. And if you do that, then you have to really struggle to get an equation of state that supports a neutron star of 2.5 solar masses. And that's tough to do. So it's either the most massive neutron star that we've ever observed, or it could be the least massive black hole that we've ever observed, right? We've never observed, actually, there's one more observation now that has a sort of similar mass, and I've just highlighted it down here, GW 200210, which has a 2.8 solar mass secondary. But if you ask people who do population synthesis of binary systems like this, They have no idea, first of all, how a black hole forms of such a small mass, and second of all, how it forms of such a small mass, but with such a big companion. And this is a really big problem for population synthesis. So you've either got one of two solutions: that all of population synthesis is not well understood, and I'll buy into that. That could very well be true. Or neutron star masses can be as big as 2.5 solar masses. And just for some reference here, this black dashed line is the 90% upper limit from that Cromartie et al. Measurement of pulsar JO740, which is 2.3 solar masses, much, much less massive. 170817, you can sort of put some upper limits on this maximum mass of around about 2.4 solar masses, depending on what kind of games you want to play. But it's really hard to get any other kinds of observations that suggest 2.5 solar mass neutron stars could exist. But we don't know how to explain this object. And I think that there's a lot of science to be done associated with really trying to understand objects like this. And of course, we've observed this other one now as well, GW200210. So this has fascinating nuclear physics application or implications, I should say, ones that I don't think we fully understand yet. But I'll sort of leave it there as an open question in gravitational wave science, and one that we sort of hope to answer in the coming years. So I'm happy to take questions if there's time, and thank you very much.
Well, just out of curiosity, do you have a personal preference or opinion about this last question? You think these are heavy neutron stars or light black holes, or you don't?
I'm almost old enough to remember when nuclear physicists told us that there was no way you could build no way an equation of state could support 2 solar masses. 2.0. I'm almost old enough to remember that. And then all of a sudden, astronomers went out and found a 2.01 solar mass neutron star, and the nuclear physicists came back and said, oh, okay, well, then I guess we can do it. And they tweaked the models. So that's my very, very skeptical way of saying, if we can figure out that this is a neutron star, I reckon that the nuclear physicists will be able to get around the huge problem that they currently have. Having said that, I think that's wishful thinking. I think it's more likely a black hole, and I think the population synthesis people don't have missed something, which would, in my mind, be a more boring solution. So I hope it's a neutron star.
Yeah. No. So when you were comparing with this tidal deformability determination, if you were comparing mainly with zero temperature equation of state, does the finite temperature treatment affect? Because I assume as the neutron star approach to each other, they start to heat up and they are not anymore cold.
Yeah, so that's a really good question. The answer is no. I don't believe it does. I'm going to just stop sharing for a sec. So I don't believe it does. Basically, what happens is when you write out the waveform for the neutron star in spiral, the leading order term away from just a point mass approximation is the lambda term. Now, you also get extra terms in that expansion. It's just that they don't kick in until the neutron stars are really close together. I think that's also the point where that tidal heating that you're asking about is also going to kick in for you to get any non-zero temperature effects. My understanding of this, my understanding is from looking at post-merger as opposed to pre-merger, but my understanding is that temperature-dependent effects on the equation of state don't kick in until you're up around 10 MeV or something like that, which is really hot. And I don't think you get to those temperatures until actually you've merged. You reach those temperatures more from the shock heating at the interface as they're merging rather than from the tidal deformability beforehand. So while it's true that the tidal deformability will heat up the star, I don't think it does it enough to change the phasing of the gravitational wave signal. But it's a really good question.
Okay.
Any other question? Is there any online question?
One question. So in these studies, you are using these waveform models. Do you also use some numerical relativity? Do we have numerical relativity simulations that may be more accurate, and or are we only using just waveform models? Like how much we can trust on these results based on what models we have?
So I missed the very start of that question. Are you asking about whether we have numerical relativity for the in spiral or for the?
I think also I think the full phase in spiral till merger and post merger as well. I don't know if we have those or not.
Yeah. Okay. So yeah, great question. So for the in spiral, absolutely, the numerical relativity simulations are really good. The waveform approximants that we use are calibrated to numerical relativity waveforms. So actually the tidal deformability there, I believe that has been calibrated to numerical relativity waveforms. And so we trust the accuracy up to some level. I personally wouldn't trust it, I don't know what the bigger effects are. There's a lot of uncertainty with a lot of these calculations, but I think the waveform accuracy for that in spiral phase is pretty good. It could be missing some physics, but I don't think it's missing much. The post-merger is a really, really interesting question. I know Tim Dietrich is giving a talk on this later today, so I don't want to spoil too much of what he might say. We have lots of waveforms. We have probably on the order of 200 numerical relativity simulations of post-merger remnants. That's certainly not enough to cover the parameter space. But to my mind, there's still a really big question of how accurate those simulations are. And the reason that I say that is they don't properly resolve some really important physics like MRI, so the magnetorotational instability. So the magnetic field is going to wind up, and it's going to wind up really quickly, and that's going to apply some magnetic torques throughout the star. And I don't think that's covered properly yet. That's going to affect, therefore, the spin distribution, the angular momentum distribution of the star, and therefore the final gravitational wave signal. So we have numerical relativity waveforms, but I think there's a way yet, a lot of research to be done to get them accurate enough. I hope that answers your question in a really long-winded way. So I apologize for that, but it's a fascinating area.
And what do you think about O4? Will we have what will be the frequency band? Can we have some events where we can see this binary neutron star and also some part of merger or close to or post merger?
Yeah, look, I'm confident with O4. So I didn't talk about O4 really. O4 is due to start. So it's the fourth observing run. It's due to start, I believe, around December next year. I can see Tom Dent's on the line. He might have sort of more nuanced information about that than me, but I believe it's, sort of this time next year, ballpark. The sensitivity will certainly increase and be better than it was in 03, but I don't think it'll be more broadband sensitivity. So I don't think you'll get more high frequency sensitivity. It'll just, that shot noise that you get up at the high frequencies, that'll come down, but not by a substantial amount to really get a post-merger signal. So I think you'll see hopefully a couple more binary neutron star in spirals. I'm not confident that we'll see a post-merger remnant. And in fact, I've got a whole series of slides. We've proposed a dedicated high frequency gravitational wave detector that it is called NEMO, because we like naming things after small animals. But we think that this is actually, it's dedicated gravitational wave interferometer up in the 1 to 3 kilohertz band to try and get post-merger signals. I personally, and this is very much a personal opinion, not a LIGO or anything, I personally don't think LIGO will get a post-merger remnant until we get to the sort of next era with 3G technologies. And Tom's just written in the chat, sounds reasonable. There will be some high frequency improvement, but not a large factor. Yeah, 05 plus maybe. Exactly. I agree with that.
There's one hand. Unmute.
Sorry, I have a very naive question. When do you talk about the temperature during the heating temperature during the merger? Can you explain to me about which temperature are you referring? I mean, like the temperature on the surface of the neutron star or in the core?
Yeah, that's not a naive question at all. That's a really good question. When I talk about and again, actually, you know, ask Tim this at the end of the day or later. He'll have a much more detailed answer. The temperature. What happens is when the two stars collide, you get this shock interface at the surface of the two stars where they really slide against each other. At that shock interface, that's where you get the really rapid temperature rise, and that goes up into the many tens of MeV, I believe. Now, I think what happens after that is that actually you get a cooler core and an outer layer that's actually a little bit hot, and it sort of almost cools from the inside out in this really weird, strange way that I must admit I don't understand at all. But that's actually a really fascinating part of, if we want to talk about temperature dependent phase transitions or anything along those lines, how that actually evolves is not something I understand well enough at all. So that it is that temperature first off at that shock interface, but once the star settles down into a fluid ball, it's the high temperature, I think, is in that sort of outer envelope, and I think the inner core is a little bit cooler, and possibly only a few MeV as opposed to sort of many tens of MeV.
So this would be like the final situation would be the opposite to the standard case where the core is hotter than the...
Yeah, I think that's right. And I think it's because of the dynamics, but it all comes out in the wash from the numerical relativity simulations.
Thank you.
Are there any comments on the chat?
Yes.
Any more questions?
Maybe I have a last question. I mean, at some moment you were talking about expectation of new signals from Newton mergers in the years to come. So the question is, how reliable are those expectations? No, on the number of new signals you expect to have in the next 3 to 4 years.
Yeah, that's a great question. Look, in terms of just the in-spiral from binary neutron star mergers, they're starting to get more and more reliable. The statistics on the number of neutron star mergers, you know, obviously the more you observe, the smaller the uncertainty on the overall merger rate. So I think in terms of the neutron star in-spirals, it's pretty easy to calculate what your expected merger rate should be, and therefore what your expected observational rate should be. I absolutely agree when you're talking about a post-merger remnant. There are things that can dampen the gravitational wave signal quicker than what we might otherwise think, which would mean that it's not emitting anywhere near as much gravitational wave energy as numerical relativity simulations show or as we otherwise expect. So until we actually observe one of these, I could not be confident that we're going to observe a post-merger remnant. There you go. You've got that on record now. It's been recorded. You know, I think that's probably the biggest uncertainty for mine, is exactly what that gravitational wave amplitude is of the post-merger remnant, how quickly it dampens, because that will affect overall what we can and can't see. And I think there's some uncertainties there that we don't understand.
There was one question of Enrique.
Enrique.
You have to.
He has to unmute.
Unmute. You have to unmute him.
He has to unmute the microphone.
Yeah, I see you've asked the question in the chat. Do you want me to, I can respond to what you've written in the chat if you like. So let me bring my slideshow back up quickly because it was about, I believe it's about slide 12. So we'll take it back. Yep.
Oh, okay, sorry, go on. No, it's just, if you can go back to that slide. There seems to be a kind of, I suppose that that the plot is sequential in time, right?
Yeah.
And there seems to be an apparent clustering in two regions, just in the 10 to 20, in the lower part of the binary of the black hole merging. Mass.
I see.
It may just be maybe yes, that and that one, yes. I suppose that has something to do with sensitivity improvements, but is this significant, or is this just a coincidence, or can you comment on that?
Yeah, that's really interesting. That's really interesting. I've never noticed that. I know that there are obviously, and actually, probably again, Tom Dent is the person to answer this better than me in the sense that he's the rates and populations guru for the collaboration, and so understands a lot of these things very, very well. I know that they're analyzed as the chunks of data, and so you can, one thing that the LIGO collaboration spends a lot of time doing, and people outside the collaboration as well, is trying to understand the mass distribution of binary black hole mergers, and you can get a lot of information about what that mass distribution is. As to the actual clustering, there certainly could be effects associated with low frequency sensitivity and things along those lines. I don't know of any that would affect this. I know that my brain can get fooled into thinking that there's clusters where there's not sometimes. I'm hoping that's it, but it's a good question. Yeah, so I don't know the answer to that. And Tom's just said he can talk to you afterwards. So
thank you.
So as we are already a little bit late, I propose to stop the talk here, the questions here. We thank you again for this excellent and very interesting talk. Thank you very much. We continue at 10 past. 3 minutes?
Yeah,
Yeah,
let's connect my own laptop.
Yeah, okay, so thank you very much. Bye.
Thank you very much. Bye.
thank you. Thanks for having me. Bye.